Okay, hello. Logic class, Friday afternoon. Let's go. Where are we right now in this class? With respect to the logic component, we have been studying propositional logic, and then just recently we have begun studying predicate logic. Okay, so let's make this chart, which I believe I've made already, but I'm, doing it again. What is logic? What is the point of logic? What do we do when we do a logic? Propositional logic is a logic. Let's discuss it. Well, first of all, it has an alphabet. What is the alphabet? Well, the alphabet, in a very formal sense, is the set of symbols which are part of the logic. And, okay, what do we have in propositional logic? Well, we have propositional variables. So those are letters which represent propositions. And usually we use capital letters for that. Okay, great. We also have the connectives, of course. So we have and, or, not, arrow, biconditional, etc. We have punctuation, so we have things like parentheses, right paren, comma. That's probably it. Maybe you want to throw in some more, bottom exclusive or something like that. Perhaps you want to get really serious and talk about brackets as well. Okay, good. I think we all know what the alphabet is. What is the alphabet for predicate logic? Well, in predicate logic, now things are sort of more complicated, right? And as we talked about last week, we have, I think pretty well, we have a lot more symbols now because we are looking inside the proposition. And so no longer thinking of an atomic proposition as a unanalyzable thing, hence atomic. Instead, we are thinking of them as composed of sort of predicates and subjects or things about which we are predicating. So, what does that mean? Well, it means that we have now name symbols, so things like A, B, C, etc. I'll leave off the commas, just I don't know why. So these are names, and all right, it's important in a kind of technical sense for it to be distinguished what is a name symbol and what is something else. And then there are variables. And okay, this gets actually quite tricky, sort of like what is a variable? We're going to see this in a minute. But they need to be distinguished. They need to be completely separate categories. And the idea is that a name symbol refers to a particular object in the domain. So it's some name like, Mr. Rose, which always refers to me. Or to give a more mathematical example, the symbol 0 is a name symbol, and then it refers to the object 0, always. It's not like something that's changing. That's true for our numerals, 0, 1, 2, 3, etc. They're symbols which refer to a particular number, whereas variables can refer to different numbers in different times. Okay, what else? These are the things which are going to sort of play the role of nouns which get plugged in, but then we also have our predicates, and so our predicates come built in with a certain number of arguments that they take. Okay, so there's no really good way of writing this, so I'll just kind of write it like this, which is to say that, maybe I shouldn't do that. Well, okay, never mind. In other words, we have predicate symbols, and this is me just trying to indicate that this particular predicate takes 2 arguments. There are also other predicates that take, just 1 argument or something like that. So we have the predicates. Okay, going too slow. I see. What else? We have all the old things except for the propositional variables. So we still have our connectives, and or, not, arrow, biconditional, bottom, etc. But then, so these are the connectives, and I see I'm running out of space here. But I also have the new things, and the new things are the quantifiers. So these new quantifiers, this one meaning there exists, and this one meaning for all, so quantifiers. And then let me just bleed into this cheat space a little bit here, because I still also have punctuation. So I still have, parentheses. Okay, this is kind of boring and obvious. And I still have equals. So equality, punctuation, quantifiers, propositional connectives, predicates, variables, names, and there's even one more which didn't come up in our previous discussion, but it will come up later, so this seems like the time for it. And that is function symbols. What are function symbols? Well, they're symbols which represent functions. Just like name symbols are symbols which represent objects, and predicate symbols are symbols which represent predicates. Function symbols represent functions. So, for example, if we're going to talk about, say, arithmetic, then addition is a function. It's a binary function, so it takes two arguments and it outputs something else. So that's also something that we might want to talk about. So, okay, great. That's our alphabet. Oh man, it's taking so long. What is the syntax for propositional logic? Well, the syntax for propositional logic is, I think, as I said some other time, it's a precise, although we are not going to be precise in this class because we're lazy, way of codifying exactly what makes this sentence good, and something like, you know, arrow, p, arrow, you know, comma, you know, that is not a syntactically valid string of propositional logic, and this one is. And when a symbol is a valid string, we call it a with, and this stands for well-formed formula. Okay, and we use this same phrase for both things, so I'll put it over there. And yeah, what is a well-formed formula? I think, as I mentioned in class, you can define this recursively via a sort of formation tree, where, you know, you basically say, okay, if R is a I'll sort of show you what I mean, like this. And then this is in turn formed from like P and Q. Okay, and so essentially what you do, if you want to define precisely, which I'm not going to do, the syntax for propositional logic, you do it recursively. You say, okay, every propositional variable is a with, and you know, if x and y are withs, then so is x and y. And if x arrow y is a with, then so is, sorry, if x and y are withs, then so is x arrow y, etc., etc. You have to be careful with your parentheses and stuff like that to make it all work. Okay, if you take a logic class in the future, this is a survey course, you might, or a computer science course that treats this kind of thing, you might see a very, very formal definition of the syntax of propositional logic, but for now, that's good enough. What's the syntax for predicate logic? Okay, it's kind of the same thing, right? Although this might be a good time for us to discuss certain sort of technical features of predicate logic, because you want to be able to say simple things like, you know, if P, well, okay, here I introduced P as a binary predicate, so perhaps I'll use Q. I want to be able to say things like, you know, Q of A and Q of B implies, you know, P of AB, say. Okay, so this is a sentence which is fundamentally kind of propositional in nature, in that it doesn't involve any variables or any quantifiers, and these three propositions are ones which once upon a time I would have called atomic, but now I'm talking about them in terms of predicate Q and sort of object A or whatever. So this is a legitimate sentence of predicate logic, of course. But the more exciting sentences are ones that say things like, you know, well, if for all x, you know, P of x implies, well, okay, here we go. I'll do something really kind of exciting. Implies Q. Okay, it's so exciting. What does it say? It says for everything in the entire world, you know, if it P's itself, then Q, or something like that. Okay, so P could be loved and Q could be, you know, something else, is happy. So if you love yourself, then you're happy. Okay, and so it's going to be quite a bit more work to construct the precise syntax for predicate logic. You want to say things like, well, you're going to have to do two recursions, right? You're going to have to say, first off, let's. This is exactly what people do. I have taken these logic classes before, where this kind of thing is done. Many times I have. And so first you have this thing called a term, what's a term? Well, a term is kind of a technical exploration of what we think of as sort of thing or object or element from the domain. So what's a term? Well, you say, first of all, every name symbol is a term. Ooh. Then every variable is a term. Those are the base cases. And then the recursive case for term is that functions are also terms, right? So if 4 is a term and 3 is a term, then you want 4 plus 3, because it's a function, ultimately returns sort of an object from the domain, so you want to make that a term as well. So you recursively define term, and then then you recursively define atomic proposition, so to speak, by saying, well, okay, if Q is a predicate symbol, that takes one argument, and you stick a term in there, then now that counts as like a proposition, a well-formed formula. And then you do all this kind of same recursive definition for all the propositional connectives, and then you also say that you're allowed to add in these things such that, like, that you want to be a well-formed formula, and that you want to be a well-formed formula as well. So essentially you just allow people to stick these two quantifiers up front. And I will say that things do actually get kind of tricky and technical in a way that we're going to not talk about. But there is a difference kind of between something like this, which is just, I guess I should keep using Q since Q takes one argument. This is kind of a proposition, right? This Q of A. Whereas if I just say Q of X, where X is a variable, then that's kind of like, what is that? That's not even a proposition. Now technically this doesn't really belong maybe in the category of syntax, this conversation, but anyway, we're just having it now. One of these is ultimately saying, A has property Q, but this sort of says X has property Q, so these are sort of in two different categories. This is a proposition, but this is sort of like not yet a proposition or something like that. You first have to tell me, what X refers to. So they're both called well-formed formulas, but they have different kind of syntactic values. And actually, there is a sort of way of talking about this. We say here that X is a free variable. And when we call this a free variable, what we are saying is that basically this variable, until you tell me what that variable is supposed to represent, because variables can represent different objects in the domain of discourse at different times, then I can't really evaluate this proposition yet, can I? Whereas this variable, and really I should draw that arrow specifically to this variable right there. When we point to that particular variable, this is a syntactic notion, so because you can define it sort of precisely based on the syntax, that this variable is free, we say. Whereas this variable is bound. X is a bound variable. Okay, and well, what does it mean to be bound? Now, this quantifier out here is sort of governing, so to speak, that variable. And so now, this variable X is not kind of waiting for an interpretation. This is sort of saying, for all X, P of X. And so, if you have the point of this notation, this will come up, one or two more times, somehow in this class, so maybe it's good to do it now, is that if you have a well-formed formula in which every variable is bound, well then that's a proposition. But if you have a well-formed formula in which some variables are unbound, then that's not a proposition. Okay, look at all this logic happening here. More semantics. So this is kind of like this. You should, the sort of fast way of summing this all up is, the alphabet is just telling you your character set. The syntax is telling you like how to, make strings, make valid strings. But the semantics is finally giving you like the meaning. So this is telling you when things are true and false, and that's kind of what meaning is. What are the semantics for propositional logic? Well, it's quite straightforward. It's truth tables. right? That's just what truth tables are. Nice, simple, happy, finite, discrete truth tables. And, you know, if I want to know the meaning of P and Q, well, the meaning of P and Q is completely contained by the truth table for it, because it's telling you under precisely what conditions that sentence is true and false. Okay, so that's pretty straightforward. Then, once you know when a sentence is true or false, then you can define validity. And we say that an argument is valid, you know, when the truth of the conclusion is guaranteed by the truth of the premises, or the truth of the premises guarantees the truth of the conclusion. Then we have a notion of an argument. So a valid argument is one in which whenever you start with true things, you end with true things. So that notion of validity is sort of after you fix the semantics, then you have a notion of validity. And only then, in my opinion, after an independent understanding of the semantics and validity, can you start talking about proof systems. And what is a proof system? A proof system is just kind of a way of pumping out valid arguments. And we spent, you know, weeks now proving things in the Fitch-style proof system, and that's what the Fitch-style proof system is. It is a system with its own precise kind of syntax and rules, which, if you follow those rules, will generate valid arguments. Okay, great. Well, moving to predicate logic, notice now this is sort of all we've done with predicate logic in class. Well, that's not all we've done in class so far. I've introduced all those technical parts of the alphabet, basically. I've introduced the syntax without going into all the details of it. And then I kind of just said, hey, you know, let's like just go with the flow and try to discover some things. And we did discover some things. We discovered, for example, that, well, what's one thing we discovered? We discovered that if there does not exist a pretty person, then it means that everyone is not pretty, for example. That's something that we talked out using our kind of innate common sense or something like that. And so I feel, very strongly this is my opinion, but I think it's true, that this is a true sentence. Now, I am using all these weird kind of words because in the propositional logic case, there was never any doubt about this kind of thing. When we thought something was true, like the corresponding sort of finite De Morgan law, which says that not P and Q if and only if not P or not Q, not only do I feel like it's true, but actually I can just crank out the truth table immediately and show you that it's true. Here, I am going to have more trouble doing this. And I want you to kind of feel for a moment how difficult this is going to be. And the reason why this is going to be difficult is because no truth table-like analysis can possibly capture the sort of depth of these quantified statements. After all, we want predicate logic to be useful even on sort of infinite domains. So, for example, we believe there are an infinite number of real numbers, and we would like to be able to quantify over them. In fact, we do that kind of thing all the time. We say all real numbers have some sort of property, or there exists a real number, you know, intermediate value theorem or something like that. And so, these quantifiers are doing a lot of work. When we say every x, we really mean for all of the infinite number of x's. And so, it's not like I can just go check them all. In fact, I can't. So, truth tables were so kind of boring because they were so easy and so obvious. And they were so obvious because ultimately every well-formed formula in propositional logic is finite, and thus the string itself is finite, and thus can contain but a finite number of propositional variables. And so it's a matter of just simply listing every possibility for each of those propositional variables that appears in that formula whether it's true or false or not, and I can sort of figure out whether the whether or not, you know, this is a tautology. But over here, I have no recourse to truth tables, and in fact, it's just simply not possible to establish by some kind of finite process whether a sentence like this is true. And also, this is meant to be, if this is meant to be a sort of basic law of logic, then it needs to apply to every possible domain, some of which may be infinite, some of which may be finite, who knows. Okay, so I'm just going to throw in a giant freaking question mark here, and I'm going to say that this is hard. Coming up with a formal semantics for predicate logic would involve the following. It would involve you giving me a sentence of predicate logic and giving me some method of determining whether that sentence is true. And if it's something like a sentence like this, if this is meant to be a tautology, then how am I supposed to check this? Well, I'm going to have to not just look at, you know, the P's and Q's now, but I'm going to have to consider sort of every conceivable, possible domain of discourse, of which there are obviously an infinite number of different domains. And I'm going to have to consider every possible different predicate. And the predicates can mean all kinds of different things. And I'm going to have to somehow talk about this infinite process of checking to see whether it's true for every single one. So this is going to be some kind of fundamentally infinite type definition. And we're either going to do this later or not in this class. But it really wasn't until like quite late, you know, like 1936-ish, that people finally got around to understanding what the semantics for predicate logic is in a kind of sufficiently sort of sophisticated way, down to the level that would be sort of equivalent to the truth table analysis. So all right, we're not going to let that slow us down. Okay. So I want to, this is an extremely long-winded introduction, but I think this is pretty high quality, of the fact that I am now going to skip semantics and go right to proof system. And I want you to appreciate how ridiculous that is, because in the typical way of presenting it, the way we followed for propositional logic, of course, it only made sense to introduce a proof system if that proof system were going to sort of reflect, echo, and in fact sort of create valid arguments. But even what it means to be a valid argument had independent justification via the semantics. And so I first learned the semantics, then I understand what a valid argument is, then I create a proof system to generate valid arguments. Well, instead, we are just going to make a proof system right now for predicate logic. And therefore, I can't convince you necessarily that the rules of this proof system are validity preserving, because I haven't even really told you what it means for these sentences to be true. Nonetheless, that's really just not a problem so much as you might think, because the semantics is fairly intuitive, and if we just kind of go with our gut feeling on this, we can create rules, and as long as we feel pretty strongly that those rules are good, then that's going to be good enough. And this is actually what all people do in normal logic classes, by the way. This is not just me doing this. In normal intro logic classes, with predicate logic at least, you do the proof system first, and the semantics you do later, or maybe not at all. Okay, that was a way of saying, hey everybody, we are going to jump right in right now to a proof system for predicate logic. And let's do it. It is the Fitch-style proof system, and it is modeled after and builds upon our Fitch-style system that we already have for propositional logic. So let's go. What was that, like 20 minutes? Oh man. Alright. I think this is significantly harder. But you're also maybe a lot smarter because you've been doing Fitch-style proofs for like a month. And yeah, so we begin. Okay, we have a rule. Well, okay. Recall that for propositional logic, we had a rule for every connective. And there was one rule to introduce the connective and one rule to eliminate it, which is a way of saying there's a rule for how to sort of prove a sentence for which that's the main connective, and there's a rule for how to extract information from a sentence of which that is the main connective. Alright, well the quantifiers are kind of like connectives in a certain sense, and so I now propose a rule, and this rule is called Existential Introduction. Okay, Existential Introduction. And, well, this one is pretty straightforward, I think. Here's what it says. It says, I'm thinking right now how I want to do this. Yeah. It says, hey, suppose you're chilling along. And, sorry. Suppose you're chilling along in the middle of a Fitch-style proof. And suppose you know that object A has property P. Well, then you may conclude if A has property P, then someone has property P. And so I conclude that there exists an X such that P of X. Okay, good. This I think is extremely intuitive. This is just what there exists an X means. It means someone has property X. And if A does, then certainly someone does. Okay, I would like you to think of existentials as infinite disjunctions. That's really kind of what they are. And so now we're going to sort of imagine over here, we're going to imagine over here a domain. Let's just imagine that we have a finite domain. Let's imagine that the domain is A1, A2, A3. Okay, so let's suppose that there are only 3 objects in this domain. Well then, then I don't really need predicate logic ever. Because, as we talked about in class, if you have a finite domain, and you don't mind taking your time, then there exists an X, P of X, should really just be thought of as, I invent a new symbol for, pretty much means that A1 has property P, or A2 has property P, or A3 has property P. And that's just what we mean when we say someone has property P. I'll just maybe do that or something. Okay, and what do we mean when we say everyone has property P, this universal quantifier? Well, then that's just saying that A1 has property P and A2 has property P and A3 has property P. Okay, and so I guess the point I'm making is if you have a finite domain, then you don't really need predicate logic, I guess. Or it's not that you don't need predicate logic, you do, because you still want to say things like this. But maybe you don't need quantifiers, and maybe you don't need, maybe you don't need quantifiers. And you don't really need variables either. And maybe you don't even need predicate logic, because you could just create a propositional variable for each of those. I don't know. Okay, well, keeping this whole thing kind of in mind, and you put like a red box around this or something, then I think there is a natural understanding of this rule, existential introduction. It is really just like the rule that says, if I know that A1 has property P, then I'm allowed to just OR stuff on. And, well, you can OR on whatever you want. And so, let's just OR on, you know, PA2 or PA3. And that, as I hopefully have just convinced you, is kind of like saying someone has property P. I think I'm going too slow here. Someone has property, if A has property P, then someone has property P. Think of that as the infinite version of going from knowledge of a particular person having a property to saying that they have their property, or someone does, or someone does, or someone does, or. It's really just or disjunction. But obviously, if your domain is infinite, then you can't even write this for all. You can't say P of A1 or P of A2 or P of A3, or if they're in fact an infinite number of objects in the domain. So you sort of have to use this existential quantifier. Okay, good. sort of too much information. Let's keep going. There's another rule, which is kind of also just sort of obvious. It's the exact analog. It says that if I know that everybody has a certain property, then I may assert about any particular person of my choosing that they have that property. So this is called universal introduction. Okay, this I don't like this heading here. Okay, so this is existential elimination, and this is universal introduction. Okay, great. What now? Yeah, what now? What does this mean? How should I think about this? How should I understand this? Well, you should think of this once again as the infinite version of something which says, if you know that everybody has a certain property, then you can point to any one person and say that they have that property. And so, imagine, to translate this into sort of the language of predicate, of propositional logic, this is like saying, if A1 has property P, and A2 has property P, and A3 has property P, well, on the temporary simplification that I have a finite domain, then I'm allowed to, by and elim, just point to a particular person, say A3, and say that they have that property. So that's all that's going on here. Universal introduction is just the infinite version of and elimination, as existential elimination is the infinite version of or introduction. Okay, that's maybe a hard concept to understand, but maybe it's actually totally obvious. Okay, next. And I need to, I think I changed this packet over the years. Sorry, 1 second. Just make sure I'm not messing this up. Yeah, what's going on? Yeah, I did. Okay, cool. Yeah, good. Okay, so, next. Universal... Sorry, this is not universal introduction. This is universal elimination. Apologies. And this is... Oh my god. I had this backwards the whole time. Yikes! 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 I don't even know what I wrote. Okay, up there I wrote introduction. Jeez. Okay. Sorry, not paying attention. I will focus. Focusing! This is existential introduction, of course, and this is, of course, universal elimination, of course. Okay, so now I want to consider, however, universal introduction. And, alright, here we go. I want to sort of prove a universal. So how do I prove that everyone has property P? Well, okay, this, I will now just lean on your experience with math, and you are all experienced sort of doing math proofs, and logic is somehow, you know, the underlying language of mathematics or something. So, okay, what happens when you want to prove, say, something about all triangles? Like, I don't know, a triangle, every triangle has 180 degrees. That's a statement about all triangles. Well, you say, okay, if I want my argument to apply to all triangles, then let me prove it for, like, the general triangle. And so what you say is, okay, well, let me take an arbitrary triangle, and you specifically, when you take that arbitrary triangle, you might give it a name, you might, you know, call it triangle ABC, but it's understood in the context of this argument to be a sort of placeholder triangle. A triangle which is meant to represent all triangles. It's a generic triangle. It's an arbitrary triangle. Okay, and then whatever you prove about that arbitrary triangle, without using any of its kind of arbitrary properties, then if that's true about all triangles, then if that's true about this triangle and you didn't use any special information about it, then it should be true about all triangles. And of course, you know, this holds in all kinds of different mathematical contexts. If you want to prove something about every odd number. Say when you square an odd number, it's odd. Well, then you take an arbitrary odd number and you square it, and then you say, oh, it's odd, so is everyone. Okay. So, how we do this is we have to prove something about, we have to prove that every object has this kind of property. So what we do is we're going to do a subproof. And the way this subproof starts is we put a little box around a letter. And what we're really doing is we are saying, take arbitrary object A. Alright, and I've been kind of stressing over this because I'm trying to, I'm considering, sort of changing my system that I've been using for my whole life or something like that. But I'm hesitant to change it, so I'm going to change it in a tiny, tiny little way. So I've been, let's see, okay. Yeah, good. Take an arbitrary object A. I'm just going to write this every single time. I think that's just all I'm going to do. So this stands for take an arbitrary object A. That's what this is. Just like we choose an arbitrary triangle, just like we choose an arbitrary real number, take an arbitrary object A. Okay. If I can prove from this that that arbitrary object has this property, then in fact every object must have this property, because I designated a sort of arbitrary object. I assumed nothing about it, and if from nothing I can show that A has that property, then everyone has that property. Take an arbitrary object A. Okay, after spending this long time being extremely philosophically careful about precisely what is a name symbol and a variable and all that kind of stuff, I shall now plead, or sort of apologize or something, that you might be asking, well, what is this? Is it a name symbol? Well, it's not really a name symbol, because it's not referring to a particular name from the domain of discourse, nor is it really a, variable either, because as I was mentioning earlier, I want this to be a proposition, and so I don't want to use a variable here, because variables are sort of would be free in that situation, and hence not a proposition. What we should call this it's an arbitrary name. But I think that's a bad, maybe that's a good name. Take an arbitrary object A. So what is this thing? This is an arbitrary name. I like that. And if you're finding this a little bit confusing, either maybe don't think about it at all, or see me for a more in-depth conversation. But this is the sort of what people do. Okay, this is an arbitrary name symbol. And it's meant to represent an arbitrary object, and we reason about it. Okay, well, I think the proof itself is very, this rule is actually very intuitive, and by the way, even can be seen as a sort of a infinite version of proof by cases. I think I'm doing that, right? Yeah, of course it is. No, not proof by cases. No, I guess it's an and introduction is really what it is. So because sort of what am I kind of doing here? I'm sort of what I want to conclude down here is everyone has a certain property, and so what I want is to say that A1 has that property, and A2 has that property, and A3 has that property, but in this sort of baby situation in which I have only 3 objects, and now how would I normally establish such a thing? Well, I would do some work or whatever, and I would establish that A1 has that property. Then I would do some more work, and I would establish that A2 has that property. I would do some more work, and I would establish that A3 has that property, and then I could join these 3 propositions together and say A1 and A2 and A3 all have that property. Well, that's what for all x p of x is shorthand for. And ultimately, you can think of this little proof here as being a kind of a shortcut or something like that to each of these proofs. And actually, there are ways in which these predicate logic proofs are somehow more elegant or simpler or something like that, because you don't kind of waste time doing something twice. This is like an infinite conjunction, and to establish this infinite conjunction, what I'm really doing is I am establishing for each of the infinite number of conjuncts, sort of once and for all in general, that they have that property. So it's sort of like a single proof of each of these three facts, kind of like at once or something like that. Then I conjoin them all together. Yeah, this is pretty good. This is a pretty good explanation. Okay. What about the final one? The final one is perhaps the most confusing and controversial of them all. And okay, with all these things, you have to sort of just do lots of practice and thinking and talking and stuff. So, okay, the final one is existential elimination. Existential elimination. Okay. And, well, what's going on here? You have an existential and you want to eliminate it. Well, what does that even mean, eliminate it? Well, eliminate means use it. Squeeze some information out of it. Extract some meaning from it. Well, how do I extract information out of an existential? That seems like kind of hard. Yeah, that is hard, because sometimes I don't know who has some property. I just know somebody does. So it's like P might be the property of, you know, what's some kind of crime that starts with P. Oh man, completely blanking on this. Painted graffiti on the wall of the police station. Okay, great. Okay, so then if P is the property, if P is the predicate that says painted some graffiti on the side of the police station, then this statement says, well, somebody did it. There exists somebody that did it. And this is the kind of thing you might say if you are investigating some kind of crime, right? Oh, I know that somebody did this thing. I just don't know who that person is. So this is kind of a natural idea here. And, well, imagine there are only 3 people in your entire town. Yeah, this is a good explanation. Well, what are we really saying when we say there exists an x such as p of x? Well, if we have an infinite domain, we're saying that one of the infinite things in that domain sort of has that property. But in this kind of little toy example, with a domain of only 3 objects, then to say that there exists an x with property p is really kind of just a more shortcut, efficient way of saying that either A1 has property p, or A2 has property p, or A3 has property p. And in fact, in a town with only 3 people, or perhaps we have 3 suspects or something like that, and the domain is the set of suspects, then if somebody painted graffiti on the side of the police station, then we can say, well, either A1 did it, or A2 did it, or A3 did it. Okay. And how can we sort of reason from there with this very kind of weak amount of information? Well, suppose I want to conclude something, and suppose the conclusion is something like, you know, maybe it was red paint which was used, and the red paint is very staining, and perhaps there were some handprints on the wall or something like that. And so the conclusion is going to be something like, you know, the perpetrator has red paint on their hand. Okay, so that's a statement. The perpetrator has red paint on their hand. Okay, and well, that might be my conclusion here. I am going somewhere with this, right? Q is now a statement that well, Q is a sort of a statement that follows intuitively from this existential. And if the statement Q follows intuitively from the the existential, then what we're trying to do is explore a way of extracting the correct information out of it to get Q. So okay, so yeah, if there exists someone, let's make the P predicate a little bit more extensive now. There exists someone who painted graffiti on the side of the police station with red paint and used very, very staining permanent red paint, and their handprints appeared on the side of the wall. Conclusion: the perpetrator, has red on their palms. Okay, well then, how do I do this? How do I get from here to here? Well, let's consider the finite case again. And in the finite case, how could I conclude this statement Q? Well, I can say something like, first we suppose that A1 is the one that did it. So that A1 has property P. And if A1 has property P, well, we can conclude that the perpetrator has red paint on their hands. And if A2 if on the other hand we assume that A2 is the person that did the graffiti, then again we can conclude Q. So what I'm doing here is a proof by cases. This is a proof by cases, and what I'm doing is I'm just going through each of the objects in my domain, each of the statements in this disjunction, and I'm trying to establish for each of these some kind of common conclusion. And if I can establish for every disjunct, if I can establish this common conclusion, then I'm entitled to this conclusion. Okay. Okay, this is kind of a modified version of our proof by cases because technically speaking, OR is kind of a binary connective, connecting just two propositions that you could imagine if we relaxed the rules a little bit and allowed for a disjunction of, sort of three things all in one big row, then you could just sort of do one proof by cases, one big proof by cases in which you explored each of the three disjuncts and then concluded the same thing. Well, it's the exact same thing going on now. What we need to do now is an infinite proof by cases. And to do an infinite proof by cases, what we're now going to do is we're going to say, okay, I don't know who the person is that has this property. So let me give them a name temporarily. Okay, and here comes the, I don't want to call it controversial, but it is maybe, it's a little bit subtle. What I'm doing is I'm once again introducing a variable, but in a totally different way from here. Here, I created a new catchphrase 1 hour ago that's going to be associated with this. High quality video here. And that is, assign to X the temporary name A. Okay. So I'm going to try to write this every single time. Assign to X the temporary name A. Chop chop. Okay. I guess I don't need quotes here. I don't know why these quotes are here. Okay. So all right. What am I really doing? I am saying if someone has this property P. That's what I know. I want to conclude from this sort of weak fact some other conclusion Q. Well, what I'm now going to do is I'm going to just simply name that person A for the moment. I know someone has this property P. I just don't know who. Well, if someone has the property P, let's just agree to call them A. Another way of phrasing this is just, call it A or something like that is really what's going on. We are agreeing to name this person X that we know must exist, name them A for the purposes of reasoning about them. And if we're going to name this person A, then of course we're going to assume the thing that we know, which is that X has property P. So let's agree to call X A, and now, so A has property P. If from this I can conclude Q, then I'm entitled to Q. And here, I just want to stress that this A has a completely different meaning than this one, though orthographically they are the same, and this has caused confusion for years. I didn't invent this notation, it's basically the standard notation. I considered changing it this year once and for all, but okay, it's a little too, I'm chickening out at the last minute. If this is an arbitrary name, I'm going to choose to call this a temporary name. I'm inventing this term, temporary name, but I think it's a good one. What I'm doing is I'm saying, let's temporarily, for the purposes of this subproof, let's name this person X A. And let me reason about this person A, and if I can come to some conclusion that doesn't have any A's in it, that's kind of important, then I can draw that conclusion. So it is important in a technical sense that, and if we look at this, you know, so A is free in Q, so people say. I've never gone into this level of detail before when teaching this, but the sort of generic statement that you conclude can't have any A's in it. That's what you'll see examples later. Okay, before I erase this board, because I do think this is pretty good explanation, if lengthy. I should just take a picture of this and just say this all one more time to compare and contrast these two proofs. What's going on here? I'm attempting to prove that everyone has a property. How do I do it? Take an arbitrary object from the domain of discourse, you might say to yourself. I introduce a new variable not previously appearing anywhere else in the proof. It is an arbitrary name. It's meant to refer to an arbitrary. It's a name that's meant to refer to an arbitrary object. Hence, arbitrary name. If I can prove that A has this property P, then I'm entitled to conclude that everyone has this property. And you should think of this as the infinite version of proving it for every single object in the domain and then anding them all together. So it's the infinite version of and intro. On the other hand, this proof is this other proof technique is how one extracts information out of an existential. And the way you do it is to temporarily name the person X that you know must exist, to give it a temporary name A. And assign this temporary name to X, then reason from there, and if from there we can conclude some fact, then in fact that conclusion must have come from the original existential. This should be, and can be, and should be thought of as an infinite version of proof by cases. What I'm really doing is, sort of in one step, the way you should view this subproof is, it is a proof by cases, but it's a proof by cases on the infinite number of different objects in my domain, sort of like in one step. Okay, good. Now we're going to do the proofs. I think I'm going to stop this video because I have to go. Resume soon. Okay, let's go. Proof 35. The numbering is 35 because this packet is meant to be a continuation of the Fitch-style packet, and I think that ended on 33. I could be wrong. Anyway, it doesn't matter. Let's call it proof 35. What is proof 35? We're going to prove our first statement in predicate logic using the logic of the quantifiers. And okay, trying to this. By the way, this is proof 36. We're going to do these both on this one board. I think we are going to. Okay, let's go. What are we trying to prove? Down here. Look down here and you will see we have this sentence. The main connective of this sentence is an arrow. And what the sentence says is everyone has property P or everyone has property Q implies that everyone has property P or Q. Okay, I'll say that one more time. If it's true that either everyone has property P or everyone has property Q, then I can say about every person that they either have property P or Q. Yeah, I feel like that's just true, right? If P is pretty and Q is quiet, then if either everyone is pretty or everyone is quiet, then everyone is pretty or quiet. Notice that this does not work in the opposite direction. If everyone has either property P or property Q, perhaps both, I cannot conclude therefore that everyone has property P or everyone has property Q. Okay, so we should be able to execute this proof, but we should not be able to execute this proof in the reverse direction. Alright, how are we going to do this proof? Well, the nice thing is that this builds upon our understanding of the Fitch-style predicate proofs. The main connective here is arrow. This is a conditional. And so the way we're going to prove this is a tautology. This is something that we're going to prove from no premises. So we have no premises in our argument, And okay, well, we're just going to, up here in line 1, we're going to assume the antecedent, which is that everyone has property P or everyone has property Q. And okay, already you're seeing that I'm using parentheses kind of like when I feel like it. In a technical sense, I should probably put parentheses around the P, but okay, I don't feel like it because it's unambiguous. And I'm concluding down here that everyone has properties sort of P or Q. Okay, so how can I do this? Well, I've assumed this and I need to get here. Okay, well, keeping myself focused on the thing I'm trying to prove, which is this one right now, how can I prove, I need to prove a universal. How do I prove a universal? Well, there's just one way to prove a universal. You pick an arbitrary object from the domain of discourse and you reason about that arbitrary object. And so, building on what we did in the beginning part of this video, I shall now begin a subproof appropriate for proving a universal. This is the universal elimination, and okay, I'm just going to look at the exact my exact phrase from earlier because I just invented it. Take an arbitrary object A. Okay, so I'm going to write this every single time. So okay, take an arbitrary object A. That is really what I'm doing. I'm choosing an arbitrary object. And what do I want to conclude about that arbitrary object? Well, I'd like to conclude about that arbitrary object that either they have property P or they have property Q. And if I can conclude this, then I am entitled, in my opinion, not in my opinion, I'm entitled by this rule to conclude that everybody has that property. Maybe I shouldn't try to squeeze this on here because it's just going to get ugly, so okay, we'll just do this. Okay, so great. Well, now I have to get here, you know, sort of from using only line 1. So let's use line 1. Well, line 1 is a disjunction, and so I'm going to do a proof by cases. Okay, so here is my proof by cases. First, I will assume, this is line 2, that everyone has property P. And, well, if everyone has property P, then, of course, A has property P. And this is an example of universal elimination. And so we say universal elimination 2. This is just the straightforward and kind of uncontroversial conclusion that says that if everyone has a property, then certainly A has that property. And now we say, okay, if A has the property, then I can OR on this Q of A. So P of A or Q of A, reason or intro line 3. Maybe I'll stick this over here. Universal elim 2. Okay. Well, so ends case 1. Now I just move directly right on to case 2. Case 2 says, well, let's consider the other disjunct in which Q, in which everyone has property Q. Well, if everyone has property Q, then certainly A has property Q. This is universal elimination 5. And then I OR a P onto the front of that, so if A has property Q, then A has property P or A has property Q, reason or intro 6. And notice what just happened here. I had a disjunction. I considered the left disjunct. I considered the right disjunct. I arrived at the exact same place, which is right here in line 8. So the justification here is OR elimination. I began with this disjunction in line 1. I did a subproof in lines 2 through 4. And I did a subproof in lines 5 through 7. And I arrived at the same conclusion. Okay, now, the big picture here is I proved in line 8, sort of from nothing, basically, I proved that either A has either property P or Q. if A has either property P or Q, then everybody has either property P or Q. And so my conclusion now is universal introduction, and it's a universal intro 2 through 8. Okay, this freaks some people out that this line doesn't get a number. Just go with me here that it doesn't really deserve a number because only propositions get numbers. And this is just not a proposition. So it doesn't get a number. Okay, and yeah, all we're really saying is, you know, starting sort of just above line 2 and ending in line 8, I did a generic proof using A as my arbitrary name. I'll even just write that down. A is my arbitrary name. That's what I'm going to call them. And using A as my arbitrary name, I proved a property that A has. So everybody has that property. And now I conclude by arrow intro, you know, that I assume something in line 1, and I concluded in line 9, so I assert the conditional. Okay, good. I erase and do 36. Let's go. 30. Well, okay, I'll just take a minute and write it down. What is 36? It says, and I'm just going to write as big as I want, that there exists an x, p of x, or q of x, if and only if yeah, this is kind of bad notation a little bit. If and only if there exists an x, p of x, or there exists an x, q of x. Okay. Shut, like that. Okay, let's take a minute and talk this out and sort of reason why this sentence makes sense. The main connective in this sentence is the biconditional, so really what I'm saying is that these two are two different ways of saying the same thing. Okay, well, what this says is there exists some object that either has property P or property Q. If there exists an object that has property P or Q, then should we conclude from that that there exists an object with property P or there exists an object with property Q? Of course there is. Because whatever the object is that either has property P or Q, then it's going to satisfy one of these. Or it's going to make one of these true. On the other hand, if I know someone has property P or someone has property Q, perhaps I don't know which, I can certainly say there is someone that has one of those two properties. Okay, so maybe that was helpful, maybe not. Talk it out to yourself in a way that makes sense. But I think this is, to me, this is intuitively valid. And so we should be able to prove it. Let's go. Fortunately, because this is a biconditional, I get to sort of lean on my background knowledge, and I'll just do what I do with biconditionals. This is a proof from no premises. So I'm going to start here in line 1 with there exists an x, p of x, or q of x. And now I will try to conclude, say, I don't know, halfway down the board or something, that the right-hand side, that there exists an x, p of x, or there exists an x, q of x. And then I'm going to sort of turn around and do it in the backwards direction. So then I will assume there exists an x, p of x, or there exists an x, q of x. Hope I'm writing small enough. And down here I will conclude there exists an x such that p or q. Okay, let's go. How am I going to do this? Let's begin. Line 1 asserts something. It asserts that there is this person. There is some person out there. What can I say about that person? Well, they either have property P or Q. And so now I hope you sort of feel in some kind of deep way that from just the knowledge that there exists some person, it's hard for me to sort of make any progress in my argument. What I really need to do is I need to just kind of give that person a name temporarily. And that's really what we're going to do right now. We're going to say, okay, you person in line 1, which I know exists, but I don't know who you are. Let's just call you A for a moment. If I name you A, then here's what I can say about A. That, you know, they have this feature, which is that either P is true of them or Q is true of them. And so now I will say my catchphrase again, which is assign to X the temporary name A. Okay, I'm just going to write this every time. Assign to X the temporary name A. The temporary name A. I use A as a temporary name for the variable X, which I know names a real person because that's what line 1 is telling me. Okay, and now that I have given this object in line 1 a name, now I can apply, you know, basic propositional logic or basic logic, you know, to these kind of facts. So either this is true or this is true. Okay, well, sounds like I should then do a proof by cases. And, well, I'm going to do that now. Better write kind of small. So in line 3, I'm going to suppose that, in fact, A has property P. But if A has property P, then I can say that there exists someone with property P. This is a basic existential introduction. Line 3. If A has a property, then someone has that property. It's a kind of a weakening of statement 3. But okay, if someone has property P, then I can make the even weaker statement that someone has property P or someone has property Q. And this is just an OR introduction from line 4. And okay, now I kind of do it again, which is to say I suppose the other disjunct in line 2, that it was Q, that A had property Q. Well, if A had property Q, then certainly there exists someone with property Q. This is an existential introduction, line 6. And then I say that someone had property P, there exists someone with property P, or there exists someone with property Q. In other words, I'm going to OR on there exists an X P of X to the front of there exists an X Q of X. This is just a straight up OR intro 7. Okay, so I hope every one of these individual steps is making sense. Now, kind of like what can I say? Well, what just happened is I was doing a proof by cases. I was doing a proof by cases on line 2, and I assumed each of the disjuncts in line 2, and from each of those disjuncts I arrived at these two kind of conclusions, which is the same conclusion. So I'm now entitled to assert that conclusion, that there exists an X, P of X, or there exists an X, Q of X. And my justification for this is just proof by cases. So I did an OR elimination. Line 2 was the disjunction that I was intending to pursue, and I did pursue it in proofs 3 through 5 and 6 through 8, and I got this line 9. Okay, now comes the part that is kind of weird. Notice how I didn't leave myself any space, because no more space is needed. I may now proceed directly to line 10. And where is this line 10 coming from? In some ways it seems like I'm just taking this line 9 and just pulling it out. And that is what I am doing. Because what is really going on here, what's really going on here is that in line 1, I knew something. I knew that there existed some kind of person. In order to pursue the consequences of that fact, I was forced to give that person a temporary name. And in line 2, I temporarily named that person in line 1A. And so, you may feel, and should feel, that this entire, I'm going to circle this now, this entire proof, subproof, every single thing here in red, was simply the exploration of line 1. It was line 1 which told me I could go into this sort of train of thought. Because line 1 says someone exists, and so now by giving that person a temporary name, I pursued some things. Well, I pursued some things, and in fact, I proved something. I proved line 9. And here's the crucial thing. Line 9 is now sort of an abstract fact that I proved that no longer has any particular reference to A. In other words, by naming the object A, and then proving a fact independent of A, then what I've shown is that that fact must just follow from line 1. And so what's really happening is that this entire line 10 really depends on line 1. Because it was line 1 which told me I could start this subproof, and I've finished the subproof with a fact independent of that temporary name that I was using. And so this fact 10 really just follows from line 1. Okay. And in fact, what we have done is we have just explored the consequences of line 1, which is to say, we eliminated line 1. So what we have now, the justification for line 10 is existential elimination, line 1, 2 through 9. In other words, I had an existential, I temporarily named that x A, kind of just repeating myself now. I did a subproof which terminated in a fact independent of A, and so now that fact simply follows back in the main bar as a direct consequence of line 1, so at the same indentation as line 1. Okay, and I was encouraging you to think of this as a sort of infinite proof by cases, and that's kind of what it is, right? What really happened in this line 2 through 9 is I took every single object from the whole town, and one at a time, I said, well, maybe they're the one with property P or Q. Conclusion, someone has property P or someone has property Q. Take the next person from the town. Suppose they're the one that has property P or Q. Well then, someone has property P or someone has property Q, etc., etc. So I've done an infinite proof by cases with every single possible object, using this temporary name as a kind of a placeholder, arriving at the same conclusion. Okay. That was sort of beaten into the ground. Hopefully that was a helpful explanation. Let's push on. What now? Well, now I have a proof by cases, and so let's just do that proof by case. Or I have a disjunction, so I'm going to do a proof by cases. First, I will assume that there is some object with property P. So assume the left disjunct. Well, what can I do now? Well, it's hard to sort of make any progress without first naming that person. So once again, I shall start a proof in which I say, let's name that person A. And I'm going to just write this every time until I get so sick of it. Assign to X the temporary name A. And, well, okay, so now I know this, I think I'm going to just drastically run out of room here. That's kind of sad. So this is P of A, so what do I get? So in line 14 now, I'm going to say, okay, well, then that means that there exists an X with property P. This is existential intro, line 13, because if A has property P, then someone has property P. And finally, I say that, oh, I think I messed up. Yeah, I did mess up. Back up a line, sorry, got distracted. If A has property P, then I'm going to now say that A has property P or Q, sorry, A has property P or A has property Q. So I want to do an or intro 13. And it's now that I want to generalize and say, okay, if A is an object that has property P or Q, then there exists an object with property P or Q. Reason, existential intro 14. And now, here's where this gets kind of maybe, I don't want to say confusing, but it takes some experience. I just have dramatically run out of room. How did I run out of room so badly? I wonder if I can fit this. I need an infinite board is what I need. What I want to conclude now is that there exists an x, P of x, or Q of x. Reason, existential elim 12, 13 through 15. What just happened here? I'll tell you what just happened. This time kind of only saying it once instead of 5 times. In line 12, I knew something. What did I know? I knew there was some person with property P. I chose to engage in an exploration of that fact. And my exploration of that fact led me to temporarily give that person, that I know exists by virtue of line 12, to temporarily give that person the name A. That's what I did here. From that conclusion, from that fact that there is this person with property P, I arrived at a conclusion that it didn't have any A's in it. And so that conclusion simply follows from line 12. And that's the extent, that's the reason why you should think of this as an existential elimination. I have eliminated the existential in line 12 in the sense that I used it. Okay, and now I just have to do that whole thing all over again somehow. So I'm just going to write really small now. So now I say there exists an x, Q of x. I temporarily give it the name. You can use new letters, or you can just keep using the same letters because they're temporary, so their use kind of expires. That's Q of A. Then I will OR on to the front P of A. Then I will sort of generalize by saying there exists an x such that P of x or Q of x. Then I will sort of indent out, so to speak, P of x or Q of x. And then down here, okay, I just ran out before the end, but I sort of don't care. This will now be the conclusion of the proof by cases. So there exists an x, parentheses here, P of x or Q of x. Okay, what's going on here? Let's perform the notations because I think they are important here. What happened? In line 17, I knew someone had property Q. I assign to x the temporary name A. Okay, great. Well, Q of A, then, because I'm saying that A should refer to the person that exists by virtue of line 17. Then I just did a little OR intro, 18. Then I said existential intro 19. Then, now that I've abstracted away from A, and so, once again, maybe I'll use green or something. Once again, I have taken information in line 17 and explored it by using the letter A temporarily to refer to the person in line 17 that exists. And from that temporary naming move, I have concluded a fact in line 20 that's independent of A. So that fact, independent of A, simply follows from line 17. And so the justification for line 21 is existential existential elim, line 17, 18 through 20. 18 through 20. So, good. I started with an existential in line 17. I explored it in lines 18 through 20. I concluded something, so that conclusion simply follows from line 17. And line 22 is the conclusion of my proof by cases. So now, note that I started with a disjunction in line 11, and I explored that disjunction in lines 12 through 16 and 17 through 21. And, okay, I hate myself a little bit because I ran out of space by one line, but please insert the final line of this proof, which is biconditional introduction, because I proved the biconditional by showing that they go in both directions. So biconditional intro, 1 through 10, 11 through 22. I'll even just write that over here. Biconditional intro, 1 through 10, 11 through 22 is the justification for the line that doesn't appear here, which shows that these are both the same. Okay, perhaps I'll just stop there, maybe, because, yeah, I think I'll stop there, and I'll assign for you for homework to do the next three, 37, 38, 39, and that'll be that. Okay, great.